Let us demonstrate the ability of Ocular to use certain examples in order to identify these use cases that we speak of. But prior to that, we'll take a quick tour of Ocular to speak of certain cases to query your code. Very quickly, I'm going to switch to my prompt. The first action that I'm going to conduct is download this code that we just spoke of. I'm going to use the example of a particular open source code called as Tarpit, which has inherent vulnerabilities embedded in this application. In order to guide our thinking, the first step of action is to compile this application. I'm going to use Maven package in order to construct a war or tar file to represent the compiler or build artifact. Now the next step is to create a graph, the code property graph that we just spoke of. And in order to create this code property graph, I'm going to use a simple command called as Java to CPG. This command takes as input the war file that we created, and as an output, it creates this composite graph representing the entire application and all of its dependencies, along with the open source framework upon which it is deployed. So in less than a few seconds, a graph is created to represent your application. Now, I'm going to drop console into Ocular, which is the query engine that lets us ask questions over this graph. Note that this graph is a security representation of your entire code corpus that we're speaking of. And Ocular is a command line tool that we'll use to guide this demo. I'm going to quickly import a series of recipes. And the first action that I'm going to conduct is load the code property graph that we just created. As the graph is loaded, now we have the capability of asking questions of the graph in scope of this interactive session. Given that the graph is loaded, the first question that I'm going to ask is list all the dependencies that we have in this application. Now with a simple API, get dependencies, I have a list of all dependencies, which are open source dependencies used by the application with its associated version. Again, with a simple command, I can filter and ask a further question if we are using a certain type of dependency. And in this case, apply a filter function and checking if the list contains a dependency with the name Jackson. Note that I'm using the name Jackson because Jackson DataBind is a very popular JSON parsing library, which is fraught with deserialization vulnerabilities. And this particular version 2.8.7 is marked as vulnerable in CVE and NIST databases. So using this very simple API, you can verify across all of your code bases of whether you are using a vulnerable open source library and take that information back to your engineers to either upgrade that library or mark this release as a risk. Now, the next question that I'm going to ask is, give me all the types defined in the code. Given that as we write code, we define types. Those types are user-defined types or language types, which are system-defined types. Now, note that by calling this simple API, which is cpg.typedeco.fullname.list, I get a list of all the types used in this application. Note that they are very interesting mix of types here. And merely by examining this list, you can quickly identify what is the code actually doing. In this case, there is a type called as zip4j, which means that the code is most likely unzipping any input received from a consumer. There is a cipher output stream used as well. So we're essentially doing some degree of crypto with our secure data associated with the code. Now we're going to further drill in to identify all literals or hard-coded elements in the application. Most often we log, and as we log, we effectively are sending messages to the log file. So in this case, I'm using an API called as cpg.method.literal.code. Again, a very fluent API. And what I get a list of is all hard-coded literals of strings in the code. Now, this is very interesting because if we see too many hard-coded elements, it most likely implies that we are not UTF compliant from a code base, which means that we cannot apply internationalization on this code, which is also not a security issue, but perhaps a design faux pas. The other danger that exists in code is often when we code really fast, there is a tendency that we might be hard coding cloud credentials in our code. And imagine if we hard code AWS keys or secrets and check into GitHub and open source our code, we are most likely at the risk of an attacker using our keys to compromise our entire cloud account. So let us ask another question to see if we have any such hard-coded elements containing AWS keys in the code. So I'm using the same method, which is cpg method literal, but here I have a pattern which is defining an AWS key expression. And it most likely implies here that there is a hard-coded AWS credential in the code, which is not good. Now I'm going to further ask if there's an AWS secret in the code. And lo and behold, yes, the engineer has mistakenly coded and left behind an AWS secret and AWS key, which is definitely not good. Now let us further ask which method of that code has this particular AWS key coded. For this, I first ask for the literal and further define the method and get the full name. So in this case, there is a particular function called as doGet in a package servlet target. So let us quickly just glance at that Java file in this code. And here it's evident that the engineer has hard-coded AWS credentials, which is not good. And even worse, he's logging these AWS credentials to the log file. So here you are at the risk of exposing these keys to the administrator of your system. And if this code is checked in the open source, you're most likely at the risk of your cloud credentials being compromised. Now let us go a step further and ask, what are the sensitive data elements that we have defined in this code? Note that this is a key value proposition that you otherwise wouldn't find in any other security tool. I'm going to quickly import this script and ask this question. But to give you a sense of the sensitive data elements, it encompasses all user-defined elements in your code. So I'm going to quickly navigate to the code base to give you a sense of what the sensitive data element is. At ShiftLeft, we have devised a technique using natural language processing and machine learning to identify all things sensitive in your code. So in this case, we have a user-defined type, which is of class user, containing first name, last name, passport number. So by glancing at how engineers name these variables, we classify this object as sensitive, and then further examine how this object is treated within your code. Now I'm going to ask the next question to identify all API endpoints in this code. So using a Fluent API, which is get API functions, it lists for me all exposed API endpoints. In this case, it is a REST application. So these are all get and post requests that are accepted from consumers or attackers. So these are the points where typically your consumers interact with, and perhaps even your attacker is attempting to exploit. So using a Fluent API, we are able to identify your entire attack surface of the application.